Now let us examine the stacking with floating point unit enabled. In fact, we had the floating point unit enabled all through, but due to lazy stacking, since we were not not coming up to this statement where a multiplication operation happened, the Cortex M4 processor actually understood that since no floating point unit was actually used, it had used only the smaller stack, thus saving on processing time. So now with this statement enabled, with this line enabled, we should see the stacking to be different, or the stack to be much larger than what we have been seeing so far. So stack will look like this now. So R0 to XPSR, this is going to be the standard one, and from there we'll see that all the floating point registers are also getting saved along with the FPSCR, and we will have the saved stack pointer here, which is not shown, but we'll have the saved stack pointer here, and the aligner is going to be here. Okay, so let's get started. Let's put this code in debug first. So we are in debug. Now let's move up to here. That is, let's continue up to here. So let's open, we can do it through the debugger. So just do a continue, and we have come here. When we have come here, let us make a note of the stack pointer. So the old stack pointer value is 2000 2B8C. So old stack pointer is okay. Now let's run the program and hit a breakpoint. That is hit the breakpoint in the interrupt service. We will disable the breakpoint here right now, because it might come into the while loop and get stuck. So this is how you do it. First, before going into the ISR, disable this breakpoint, and when you are coming out of it, then enable the breakpoint and catch the control here, and then do your examination. Those are the steps. So right now I have a breakpoint here, and let's continue and see what happens. So we have the control come to the sysdig handler. Okay. Now when the control has come to the sysdig handler, we will see what is the new stack pointer value. Now the stack pointer value that we see here, or if you want to print the stack pointer here, you see the value is 2000 2B1C, which is different from what we saw in the previous case. So the new stack pointer in our case here is is 0x2000 and then 2B1C. Okay, so if it's 2B1C, that would mean that the stack is, anyway we can see from here that the stack is much bigger. So 2B8C to 2B1C. So we know it is 70, but then nevertheless we'll just run it on the calculator. So 2B8C minus 2B1C. So it is 70 hex. 70 hex would mean 112 decimal. Okay, so let's write that down. So 70 hex. So the value is, so we'll always do the old minus new, SP minus new SP equals to 0x70 hex, and that value is, as we saw, it is 112 decimal. So we'll just write it down. So it is 112 decimal. So if it's 112 decimal, now let us see how many words are there in 112 bytes. So 112 divided by 4, like we did in the previous case. So 4 2s are 8. Okay. 9, 10, 11, 4 8s are 32. So we have 28 words here. Okay. So we can see 28 words in this case. So we can guess, if we look at the disassembly now, let's have a look at the disassembly and see, it will give us an idea of where to look from. So it has just pushed R7 because we have this toggle LED disabled. So there is only one extra space occupied in the stack over and above what has been saved for the floating point stack. Okay. So out of 28 words, we'll have one word less. So we'll have 27 words. If we had any function call within this, then this would be 29 words, because there will be a push of 2 values here. So you have to do your calculation and investigation accordingly. So currently we have 28. So 28 minus 1 is going to be 27. But we will see all the entire 28 values here. So what is the current stack pointer here is 20002B1C. So here it is going to be X, and then how many words are we checking? We are going to check for all the 28 words, right? So we'll do 28 X and then the stack pointer, $stack pointer, and we get this value. Okay, so now it is quite, I would say this value is quite overwhelming, but then this is exactly what, so let us count how many values there are right now here. So we have 1 2 3 4 5, just a moment, let me expand this a bit so that we get the whole thing. 1 2 3 4 5 6 7, 1 2 3 4, so 7 into 4, 28 values are being printed here, out of which we know that the first value, like we saw previously, is the one that has been pushed by the here. So it's written by the compiler. So this is not what we are, this is not, we are not interested in this value. Our stack actually starts from here. Okay, so this is where the values stack started from. And so let's see. So 2B1C is the current stack pointer, but then our actual value of interest is this one. But mind it, the stack has started getting filled in this direction, this way. Okay, because this was the higher address, so it went on getting filled in this way, and it came up to here. So and we saw that in the slides. So it would have, if you look here, it would have started getting filled in this direction. All these values got saved, and then it came up to R0. So when we investigate the stack, we have to obviously investigate it in that way. So this value would be R0, R1, R2, R3, R12, LRPC, XPSR. So this is as is, R0, R1, R2, R3, R12, LRPC, XPSR. So, and we can recognize this value also from the previous case, this one. Right? So XPSR value looks like this. And the rest of the values that you're seeing in these memory locations are the stack values for the floating point registers. But we will observe something here. The values that are here really are not the same as what we see here. That is S0, S1, S2. So S0 starts from here, and we see that the values are quite random. They are not the same values as what we see here. So even though the stack space is reserved, the values have not been pushed to the stack. So that is another feature of lazy stacking. For example, if you see S15, which is 47.55377796, and if you check the converter, we should see some value like this 0x423E3712, which should have been saved on the stack somewhere, because that calculation had happened in the main. But we don't see that value anywhere here. Nothing, no value starting from 4 is seen anywhere. Now the reason behind this is, as I stated, is because of lazy stacking. So there is a floating point instruction that is being used in the main. So stack area is actually reserved for floating point. So it has reserved 28 bytes, in this case 28 bytes. And then what we see is when it comes into the interrupt handler, this register has the value of this 47.553, the answer, but that value has not been pushed to the stack. So the reason behind this is Cortex M4 is still trying to save some clock cycles, because it knows that in the ISR the floating point unit is not being used. So why just save all those registers in the stack and then restore them? Let's save so many cycles. So let me leave as S15 as it is and not bother about it anymore. So when the control goes back from the ISR to the main program, this register is not touched, so this value is retained. However, if we are doing some operation on the floating point registers in the handler, then the Cortex M4 knows that now is the time that these registers, the old register values, have to be pushed to the stack. So now is the time for pushing those values into the stack. It cannot be lazy anymore, because those values will be used for newer those registers are going to be used for newer calculations. So it has to save it. So that is when it actually starts saving the values here. So we'll stop the debug here, and we'll add some statements here so that the floating point unit gets used, and we will re-examine the stack. When we come back to the stack again, we will see that maybe the stack size would change, because the stack size would change. Maybe it will become higher, because at that time some padding bits might be included when we add some lines of code here. So the size of the stack may not remain the same. We'll have to do the stack calculation from the scratch again, and we'll see how the including some floating point instructions into the sysdig handler changes the look of this stack. So we'll have it looking different once that happens. So let's do that. So what we need to do is I'll just copy these two lines over from here to here, that is, and probably make some changes. So just let's say test float underscore ISR, and then test float underscore ISR, and then we, instead of multiplying the value by 2, we say multiply the value by 3. So it's a different expression now. Save this. Okay, and we will restart the debug session. When we restart the debug session, we will have to do the stack size calculation all over again, but we'll do it. So let's stop the debug session now. And restart it. So when we restart the debug session, there is going to be a recompile because the code has changed here. So now floating point is being used here and floating point is being used here in both places. So what we do is we'll run the code as we do. So let's get into the debugger console and type C continue when it comes and hits this breakpoint. So we are using a float value here. Then we will continue once again, and then we come and hit the sysdig handler. Okay, so I committed a mistake. Let's rewind, just reset the chip because I forgot to take the initial stack pointer value here. So let's do that. So we'll check the initial stack pointer value here. So we'll do we are here now. Now let's make a note of the stack pointer. So we do p $sp, and here this time around we are seeing that the stack pointer value is different. So that's okay. Let's go with that value. So it's 20002B7C. So let's go with that value, and then let's resume and let's hit the breakpoint in the sysdig handler, and let's check the stack pointer value once again. So it is 2B00. So let's see what is the size of the new minus the old stack pointer. So let's do that. So we'll have to do 0x 2000 to B7C minus 0x 2000 to B00. So we can straight away see that the value comes to 7C. So let's see what 7C is in decimal. We have done a calculation previously, so let's say 7C is 124 in decimal. So that makes the stack of 4 3s are 12, 4 1s are 4, 31 words. Okay, we have just one value that has been pushed by the compiler. Okay, so 31 would mean 30 floating point stack would be 30 word long. Okay, so let's see, let's print the stack and see what we get. So we know it's 31, so we do x/31x now $sp. So we get the stack pointer value and the actual value that was saved. Okay, here we have all zeros, and the first save, that is this one, actually starts from here. Okay, so there are some values which are unused, which are becoming a part of the stack. So these could be padding bits, and it is sysdig handler just has a push R7. Okay, there is no so from 31 from 31, if we take away 1, it is 30, but then we have these 3 padding bits. So if we take this away, we again have 28 starting from here. So 28 starts from here. So padding, this is the push of the old stack pointer, which has been done by this assembly instruction, which was this instruction was put in by the compiler. This is from where we actually start the count. So this is R0, R1, R2, R3, and so on. Okay. So let us have a look at the stack, how it looks for floating point enabled. So we have the bottom part is the same, R0, R1, R2, R3, R12, LR, PCX, PSR, as we saw previously. And then the S0, S1, S2, S3, S4 starts up to S15. So 1, 2, 3, 4, 5, 6, 7, 8. So we take 8 values here, 1, 2, 3, 4, 5, 6, 7, 8. And this is from where the floating point stack registers address space starts. And we see again, like previously, that we don't see the saved values. Yes, 15 is 47.553, and we don't see it here. We see none of it here. That value is absent. So the Cortex M4 is still lazy even now. So let's single step. We'll not set a breakpoint. Let's single step through these instructions and come up to here. So we'll step over and we'll come up to there, and we'll see what we get. So we have come one instruction. Let's print the stack and see. Same instruction. Let's print the stack and see if the value has still come or not. As you can see, this value has still not come. So we are judging by only this value, because that is where if we see this value come on the stack, we'll know that it has started the saving of the value. So that is the reason we are hunting for this value. Now let's proceed. Let's step one more. Now let's see what has happened. Now let's print the stack once again here. So this is the old one. This is not going to change on the fly like this. We are just taking print in GDB. So let's print the stack once again and see what we have got. So we have got 423E3712 here. Okay, now let's check. Can you see this value here? 423E3712. So now when it saw this instruction, the controller saw this instruction, it knew that, okay, I cannot be lazy anymore, because I ran these two instructions, or ran these two lines of code here. So it has to use those floating point registers within the ISR, as you can see here. So these values, the old values, now have to be saved. So there is no other option but for it to save those values onto the stack, and this is what you see. So now the values have come in appropriately onto the stack. We saw some random values previously, but now if you see, we have most of the values are zeros, and this value, that is the S15 value, is what it should be. So now it went ahead and did the stacking. So let's have a look at the stack, how it looks. So it's S15 FPSCR. So it's S15 and then FPSCR, and there's again there's some padding here. So this is how the lazy stacking works for Cortex M4. It's a little confusing. When you try it out also, you will be confused as to how this thing is carried out, because you will have padding bits in the middle, and so many things do happen here. But at least we understand the concept now, that within the handler, if you don't have a float operation, it will reserve the space for the stack, but it will still not fill it. Only when it encounters a float operation inside the SysTick handler will you see the values being stored onto the stack, and that is when you see the values come up here.